This meeting is being recorded.
Yeah. So respected senior members of INS and friends, it gives me an opportunity to welcome you all again today's for yet another weekend webinar. It is indeed a delight to engage members in scientific deliberation and talks, which is refreshing to all those who are participating. INS continues to provide information about the development and status of science and engineering, and in particular about nuclear science and technology. The webinar series has given opportunity to wide-ranging speakers with diverse expertise to address our members. Both the speakers and members have enjoyed the exchange of information through discussion that ensue the presentation. Today we have with us Shri Arun Kumar, Deputy Manager, Research and Product Development and Advanced Technology Development, BHEL Trichy, who is going to talk to us on challenges in design of nuclear power plant components. This is a very important topic for the designers in NPCIL, Bhavini, and High Water Board, etc. On behalf of INS and on my own behalf, I welcome you, sir, to this 31st INS webinar. I thank you for agreeing to give a talk to us today. And I must mention that our Arun Kumar was in NPCIL and he returned to NPCIL Mumbai office and he returned to Trichy only yesterday. That's what he told me just now. It is a pleasure. It is a great pleasure indeed to listen to you, young officer, about the challenges he is facing in designing nuclear components. Viewers may recall that there was an extensive discussion during the annual conference in March 2020 on aspirations and expectations of the industry partners and NPCIL, whereas industry strongly argued about lack of flow of orders and NPCIL countered with a lack of quality in manufacture and frequent change in the team members. NPCIL CMD particularly requested industry partners to deliver strictly as per the strict component specification to avoid rework or rejection. There seems to be a lot of room for improvement from both the sides. I'm sure they are being addressed at all the levels. Both have to work together for the success of the projected targets for supply of clean energy. I am sure Shri Arun Kumar will touch upon several aspects of the industry. I welcome you, sir, again to this webinar platform of INS. Now, before I request Arun Kumar to give his presentation, I request our President, S.K. Mehta, to give his opening remark.
Well, thanks a lot, Dr. Kumar. Let me join you in welcoming Arun Kumar. Now, the design of the nuclear power plants has brought in many challenges, not only in manufacturing, but in engineering, in the quality assurance, in documentation, in materials, fabrication, and other things that's on materials, quality assurance. So there are many, many areas in which the nuclear energy has penetrated and upgraded many quality design requirements, and new technology has come in. It is really a pleasure for me and for all of us to listen to Arun Kumar, the kind of challenges he has faced in the design of nuclear power plant components. So welcome you, Arun Kumar.
Sir, thank you very much.
Yeah.
Thank you very much, Ramarao sir, and thank you very much, Mehta sir, for your invitation. So, shall I start my presentation, sir?
Yeah, please go ahead. Go ahead.
Okay, sir. Sir, actually, since
Arun Kumar, you are out of presentation. Can you share it again? Arun Kumar? He got disconnected, I think.
Yeah, he is disconnected.
Yeah. He'll come back. Yeah, he's coming. Yes, you are connected. Now you please share. Mute yourself. Unmute yourself, please.
Is muted. No.
Yeah. Yes. Make a slideshow. Yeah, continue.
Oh, okay, sir. Sir, actually, since we are working with many projects on BRC and LPCL, and we have secrecy agreements with BRC, so we never presented in a public forum like this. So this time our management has given me this opportunity to discuss the challenges what we are facing. Sir, am I audible, sir?
Yeah, you are. You are.
Can you kindly speak a little bit louder, please?
Okay, sir. So this is the first time in my career I am presenting in such a forum with all seniors, and I'm going to discuss about some of the challenges which really has to be addressed or we faced, and we could not even the code ASME. We follow ASME for our design section 3. Subsection division 1 and subsection NB. Some of the aspects were not addressed in code. So those things I will share with the forum. If I get some guidance on how to overcome these challenges, it will be helpful for me, sir.
Sure, sure.
Okay, sir. Sir, this all you may be knowing, these are all the major milestones of manufacturing a component for a nuclear application. Now, I'll just give a brief introduction or brief details about how uh, design is changed from time to time in ASME code. Then, what are all the material procurement issues we are facing and how it affects our design of this nuclear components, and I will briefly touch upon what are all the process which uh, which uh, affects our design and how it has to be addressed. What are all the aspects which are not covered in code or where we are being structured in design. Then what are all the quality control aspects, even packing and dispatch, which affects our design process. So I want to give you some ASME evolution, how the evolution has been made in the uh, with historical changes in change of factor of safety, sir. For example, this everyone knows about factor of safety. This is the cushion given for the unknown factors in the design. So when the first edition of code ASME was released in 1914, the factor of safety was 5. So this was till in 1944, the factor of safety was 5 only. But in 1994, due to Second World War, there was a scarcity of materials. So what happened? The factor of safety was reduced from 5 to 4. That means, uh, actually, if the design requirement for the actual observed stress, if the requirement of thickness for a pressure vessel is 20 mm, we have to give 100 mm thickness with a factor of safety 5. Then, since the factor of safety has been reduced from 5 to 4 from 1944, so we can use only 80 mm thickness of the pressure vessel, which give 20% of material saving. And also the hydrotest pressure was changed from 2 to 1.5 due to this change in factor of safety. But since the change was war driven, not the technology driven, the factor of safety has been again changed to 5, or it has gone back to 5. So in 1951 addenda, They have reviewed the power plants or pressure vessels which were designed with a factor of safety of 4. They were extremely performing well compared to the pressure vessels designed with a factor of safety of 5. So the factor of safety was permanently reduced to 4. This was done in 1951 addenda of the code. So in 1996, the chairman of ASME code committee has reviewed this factor of safety. Here, 5 major improvements were considered at that time. So the first improvement is metallurgical aspects of steel making process. For example, small additions of molybdenum to carbon steel prevents graphitization. Then small or addition of chromium to the steel gives corrosion resistance. Then influence of manganese controls the detrimental effects of sulfur during welding. Then there were very much advancements in welding. For example, uh, in recent days, we use many techniques like gas metal arc welding, GTAW, that is gas tungsten arc welding, electroslag welding process, electron beam welding process, laser beam welding process. Those techniques were not available in before 1944. And non-destructive examination till 1935, X-ray radiography was the only examination, non-destructive examination. That too, it can detect up to 100 mm thickness, or it is effective in up to 100 mm thickness of the material. So in those days, the thickness of pressure boundary was restricted up to 100 mm only. Then nowadays, many techniques in LDE has been developed like PT, UT, MPT, even UT detects the thickness of the material, and eddy current examination, which gives wall loss in the material. So these developments have been reviewed in 1996. Then fracture mechanics developments, like in the allowable stress, initially yield and ultimate with the factor of safety was considered. That is the primary stresses. Now the secondary stresses like creep, fatigue, ratcheting, those are under consideration, and due to which the allowable stresses were redefined. And also the post-well heat treatment, preheating, post-heating was not there till 1962 edition of the code. Now, uh, these locked-in stresses due to non-uniform heating and cooling of the material during welding or during various manufacturing process like thermal cutting and all has been relieved by appropriate post-well heat treatment or preheating, post-heating of the material. Based on these, based on these developments, the factor of safety has been reduced in 1996 from 4 to 3.5. Now, the factor of safety for nuclear application is 3. So, we have to avoid all the unknown factors in our design, from material selection to bill dispatch of the equipment. Now, let me come to material selection, how it impacts the design. First, in nuclear application, there is a process called irradiation. That is the process of material exposing to the radioactive environment is called irradiation. Due to irradiation, what happens? The nil ductility transient temperature of the material is getting increased. It is the temperature at which the material loses its ductility and behaves as a pure brittle material. So, some of the materials like austenitic stainless steels and titanium alloys, in which the increase in nil ductility transient temperature due to this irradiation is negligible. So we have to use these materials necessarily in the new components designed in the primary side. But what happens while we use austenitic stainless steel? The strength at higher temperature is it comes down in case of austenitic stainless steel. So we have to go for ferritic stainless steel in uh, ferritic steels in nuclear applications. So whenever there is a primary coolant is in contact or radioactive fluid is in contact with the material, there we have to do cladding with austenitic stainless steel. When we perform cladding, uh, due to the difference in thermal conductivity of both the materials and heat transfer coefficient of both the materials, it creates some thermal stresses to the material that has to be encountered in design properly. Now I'll explain you one our real-time problem. If I get some solution, it will be very much useful for our nuclear industry. Uh, that is for all our materials. Before use, we have to establish the RTNDT. RTNDT temperature means reference mill ductility transition temperature. There is a standard ASTM E208 in which we can establish this mill ductility transition temperature through drop weight test. For example, I'll explain you for a material, this RTNDT is being established through drop weight test. For example, here we are conducting one drop weight test at 0 degrees Celsius. Then -5, it has to be conducted with a difference of 5 degrees Celsius. At a particular temperature where we are getting no break in both the specimens, plus 5 degrees Celsius will be considered as the TNDT, that is NDT temperature. Then we have to perform impact test at plus 33 degrees Celsius. For example, minus 25 degrees Celsius is established as our TNDT. We have to perform impact test at plus 33. That means minus 25 plus 33, so plus 80 degrees Celsius. If the impact test passes with the impact energy level of 68 joules and 0.89 mm lateral expansion, then that temperature, that minus 25 degree, will be called as RTNDT temperature. Now I'll come to my problem. In the problem what we are facing at our industry, we are procuring pressure boundary forgings from various suppliers, and they are providing, they are taking some coupons as per code at the top or bottom of the forging as per the code requirement. Now they're establishing this RTNDT at their works based on this drop weight test. For example, they are establishing minus 30 degrees Celsius as uh, uh, drop weight test, as RTNDT temperature at their works, and we are getting the same coupon. That is called raw material test coupon. That test coupon is undergoing uh, all the process which undergoes, which the original job undergoes. For example, we are manufacturing a steam generator. It undergoes 2-3, that particular component or that particular raw material is going to undergo 2-3 heat treatment cycles. So this coupon also heat treated along with the job. Then again, once again, we are establishing this RTNDT. What happens when we establish this RTNDT temperature at our works after the actual heat treatment of the material? The RTNDT temperature has crossed even 30 degree. For example, it crosses sometimes uh, uh, 10 degrees Celsius also. Sometimes we have established plus 20 degrees Celsius as RTNDT. However, the same was established in STC. STC means simulated heat treatment coupon. They will do a heat treatment with a longer cycle, or the worst cycle, the component which is undergoing manufacture will undergo heat treatment. So after that heat treatment, they have already established that is minus 30 degrees Celsius, and what we are establishing is at plus 20 degrees Celsius. That means around 50 degree Celsius difference also we could identify. So I want to emphasize on this is this affects the performance of our equipment which is designed for the nuclear application. Then we have done so many root causes and all, and we could find that the uh, heating and cooling rate in the heat treatment cycle influences the uh, ductility of material. So that is the reason why we are getting RT at very high temperature. So in code, there is a section in ASME, section 3 MB, that is 4600, in which there are requirements given for the heat treatment. There, there is a rate of heating and rate of cooling. There, they have given some guidance, that is the rate of heating or cooling at any hourly interval should not exceed 220 divided by thickness in inches of the material being heat treated. So we are going as per the code requirement, and we are taking the worst condition. For example, in a heat treatment, if there are some six number of weld joints included, so we will be taking the weld joint with the lesser thickness of weld. So sorry, very higher thickness of weld. So what will happen, this rate of heating or cooling will be very less. So that we will consider as the rate of heating or cooling for that particular heat treatment cycle, and we will perform the heat treatment. What happened when we test after this heat treatment, the test coupons, we are ending up with loss in ductility of the material. So this is one of the major concern we are facing in material selection, sir. Then the second point in heat treatment of the raw material, there is based on the P number of the material, there is uh, particular guidance for minimum soaking time. But the maximum soaking time, or since the power cut during soaking or during cooling cycle, if it is in heating cycle, once again the heat treatment will be continued. If in case if a power cut happens during soaking of the uh, uh, material or cooling rate of cooling in a particular heat treatment cycle, guidance is not provided in our ASME code, and much literature is not also not available. This because in foreign countries they might have not even envisaged this power cut during heat treatment. What happens whenever a power cut happens? We are during heat treatment we are going again for the uh, uh, heat treatment of the total equipment, even that may be having the weight of around 50 tons or 100 tons. Again, we are going for one more furnace heat treatment that deteriorates the ductility of the material. So this is one of the major concern we are facing in design of nuclear components for nuclear power plant applications, sir. Sir, at the end of my presentation, if I get some guidance on this, it will be very helpful for our BHL, not only to BHL, to the nuclear society, sir.
Okay.
Okay. Sir, then let me explain how the process affects our design. Since already I explained you, we could not use austenitic stainless steel material for the pressure boundary for high temperature applications because of two reasons. One reason is the reduction in strength at very high temperature. The second reason is uh, what happens, this osmotic stainless steel compared to the carbon steel material, the thermal conductivity is very less. So the delta T in a thermal stress, the formula you all may be knowing, sir, E alpha delta T. Here the coefficient of thermal expansion is also higher. Then due to lesser thermal conductivity, this delta T is also higher. So whenever we increase the thickness for the higher stress, since here the thickness and the stresses are directly proportional, whenever we increase the thickness of pressure boundary, the thermal stresses are getting increased. So we could not arrive at a optimum uh, material thickness. So we go for ferritic steels and we are going for cladding. What happens when we go for cladding? Sir, here I have shown one photograph on a district in which we have done cladding on the material. What happens? We are getting some defects in UT or RT in the interface between this ferritic material and the cladded material, that is austenitic stainless steel. So if we get a defect in the interface while making a groove for repair, we have to take some more material in the uh, ferritic material. So this cladded material is not taking any load in the design. Only the ferritic material takes care of the uh, various stresses during the service of the equipment. So what happens here? We are going for loss of material thickness here. Then if we deposit again the ferritic material to compensate for this thickness loss, what happens? Whenever there in the nearby region already cladded material is there. So in the region where it touches, the ferritic deposit touches the this cladding, there we are getting more number of indications that could not be identified whether it is a real indication or some kind of spurious indications. So what we have done, I have shown a figure. This issue we have resolved ourselves, that here we have taken a groove, wider groove near to the actual repair groove. Then we have deposited this ferritic buildup uh, that is made uh, zero point 0.5 to 1 mm beneath the cladded already available cladded deposit, so that we are keeping this ferritic as well as this austenitic material to touch with, so that we are avoiding this. But we are in this case we are losing 1 mm thickness in the pressure boundary. However, this we are managing, sir. This may be helpful for you in while working on this cladding in some other nuclear applications, sir.
Arun Kumar, can you use a pointer wherever possible?
Sir, can you able to see the
Yeah,
pointer?
yeah.
Sir, actually, this portion which is shown as cladding is the cladded region, and this hatched region is the parent material. Okay, sir. Here in the interface, if we get a defect, so if we make a groove like this, as we do for any repair grooves in case of UT or RT repair and further build-up, whenever this ferritic buildup touches this inconel or austenitic stainless steel cladding, it gives in this region large amount of spurious indications or non-relevant indications. So what we have done, we have made a wider groove like this, sir. Instead of making a groove as we do in the other cases, we have made a groove like this. And this ferritic deposit, which is actual to this parent material, we have done this deposit. But we what to say, we we have restricted this buildup below 0.5 to 1 mm than this actual cladding, so that we are avoiding these indications. Then for the remaining region, we do the buildup of cladding, actual cladding material, that is austenitic stainless steel. This is how we have overcome from this cladding issue, sir. Shall I move to the
Yeah,
next
yeah,
slide, sir?
yeah. Please go ahead.
Sir, in one of the nozzle, I could not show you the total picture over here, sir, because of our secrecy agreements. So I'm sharing you the details, technical details alone here, sir. So here, what we are, this is one of our steam nozzles, sir. Actually, whenever we go for austenitic stainless steel, we are getting one more problem, sir. That is stress corrosion cracking. Whenever there is a, susceptible atmosphere of steam water mixture and some tensile stresses that might have been developed during our manufacturing also. So for austenitic stainless steel material is prone for stress corrosion cracking under steam water atmosphere. So so what we are doing over here, we are making an austenitic stainless steel build-up, and we are welding the material over this. So as per code, minimum 5 mm uh, cladding is required. But we have developed some weld techniques, and we could able to get the austenitic stainless steel chemistry at 4 mm thickness of the weld joint, or 4 mm thickness of cladding. So we were trying to weld this cladding with austenitic stainless steel material. What happens whenever there is a, minor repair on this austenitic stainless steel? So we used to make grinding and build up, or if we get a small PT indication, to remove those PT indication, we used to do grinding of that particular region. There, the thickness is getting reduced, sir. If the thickness of cladding is getting reduced, what happens? This we have not foreseen during our design process. When the actual welding in shop has happened, they have removed the PT indication. Now the thickness of this cladding has been reduced to 3.5 mm, for example. There, the material is in between the ferritic and austenitic. So the weld, it cracks in that region, because we are, since austenitic stainless steel weld doesn't warrant for any, doesn't require any post-weld heat treatment as per code. After this welding, we are not going for any heat treatment. So whenever we test in the PQT, we were getting some cracks or some indications in some of the regions. So we have done many RCA, root cause analysis, to find out where is the mistake. Then we could find that in shop, practically they could not make minimum 4 mm thickness all over, or for the total circumference. So what happens? The region wherever they have done some rework, it is not noticed during the what to say, while checking the thickness uh, by uh, by any relative method to find out the thickness. So what happened is, there we got many cracks and indication. Then we found out that uh, we have to give some more cushion for the welders or for the process. Then we have increased this cladding thickness, and we have remodified our design. We have done lot of uh, uh, CFD to, for this modification of, or reduction in ID of this particular material. and we came out from this problem. So this is how in nuclear industry, each and every small aspects of process affects our design, and the design has to be remodified. Then quality control. Now let me explain you, sir, about our hydro test. Initial days, the hydro test was done at 1.5 times the design pressure. Now it is reduced to 1.25 times of design pressure. However, the limit for this hydro test is 90% of the yield stress. But what happens for since we are using these components for nuclear applications, the hydro test to be conducted at very high temperature. For example, because of this RT-NDT problem, which I have explained you earlier, the hydro test to be carried out at plus 33 degrees Celsius. That is RT-NDT temperature plus 33 degrees Celsius. For example, in some of the case, if the RT-NDT in it is as a rare case in only one component we got this problem, that is 30 degrees Celsius RT-NDT temperature. So what happens? We have to do hydro test at plus 63 degrees Celsius. So uh, that is not the water temperature, that is the minimum metal temperature of the pressure boundary to be tested at plus 63 degrees Celsius. So we have to employ a huge amount of heating arrangements for the liquid. The total amount of liquid to be used is around 120 tons, 120 metric tons of water. So we have heated the water and we have circulated for very long time. Then only we could achieve this plus 63 degrees Celsius minimum metal temperature. And not only that, we have heated in the high mass areas to improve this temperature. So what happened? The stresses, yield stresses, or the stress strain curve is coming down at higher temperature. So we have not considered this aspect of plus 63 degrees Celsius metal temperature during our design. Then only we could find out that for this pressure, the uh, at that this particular temperature, we have again relooked our design for hydro test for all the pressure boundary components. So our to uh, to check whether all the pressure boundary are able to withstand this hydro test pressure at this particular temperature. So it uh, uh, this has made our steam generator to wait for some more time to finalize this design and proceed with the actual hydro test. Then the eddy current examination of tubes being used for our heat exchangers involved in nuclear application. What happens? This eddy current examination sometimes gives the percentage wall loss, that is percentage wall thinning uh, uh, in some locations. When we do boroscopic examination or when we cut the sample, we could not identify any defect or any variation in the surface at that particular location. So what we did was that the change in impedance, change in current, everything gives some spurious indications in the eddy current examinations. So we have done a lot of research and we found out that some of the indications which doesn't form a proper loop or not uh, or it is not harmful or it is harmless for the design. Then in some of the cases when we based on the after eddy current examination, if we do boroscopic examination and if we do some ID polishing or some rework, what happens? the thickness at the particular region comes down. So here our design is very optimum, uh, so that what happens, it doesn't reveal any percentage wall loss in the subsequent eddy current examination, but it reduces the thickness of the material. So what happens, the design thickness is coming down. So in service, this may create some problem to the tubes which are so these uh, uh, but we cannot reject at the for a small very fine scratch at the after the manufacturing of the particular steam generator or heat exchanger. Anyway, we have to do uh, some kind of rework, and we have to make this tube to contribute for the heat transfer in service. But in design stage, these are all the factors we have to take or we have to consider. This comes during our experience in manufacturing only. So we have introduced some 0.1 mm thickness in the design at later stage based on these experiences. Then in packing and dispatch also, it affects our design. For example, the equipments which is designed for nuclear applications has to be dispatched with nitrogen uh, in filled in condition in the equipment as well as the outer periphery of the equipment. So we have to make very huge massive structures. Then we have to keep our equipment, then we have to fill with nitrogen. What happens here uh, uh, in transit, or due to some, we are not giving adequate focus for the filling lines or the transportation or this nitrogen gas filling lines, or the lines which is used for the gauge during design. What happens, this nitrogen leaks in some cases during transit. So during transportation, even though we attach a cylinder, since the volume is very high, we could not uh, fill up immediately. So what happens if the nitrogen leaks and uh, the pressure comes to the atmospheric pressure, the air. Sometimes the transport may happen through near to the sea and all. So the atmospheric air can go into the outer containment or to the component, and it may do some corrosion to the equipment. So based on these experiences, in leakage of this nitrogen in some cases, we have improvised our design. Uh, so this also, even packing and dispatch also gives some improvement in design. Now, this is our overall overview of our steam generator, which we are manufacturing for 700 megawatt steam generator. Even this is available, this uh, uh, design aspects or the 3D views of the steam generators are available even in the public domain. Now let me explain you how we are doing design and what are all the problems we are facing in various aspects of this design. First, we are doing 1D thermohydraulic sizing. This is being done to optimize the design to find out the number of tube length, and various sizes, various heat transfer and pressure drop. So here in initial stage, this has been done through an inbuilt code at the beginning when BHEL was developing this steam generator in 235 megawatt and 500 megawatt. At the time, we were not considered this 3% boiling. There is a scope of 3% boiling that also gives some amount of heat transfer. So that we have considered in case of 700 megawatt, based on which we could extract from the same uh, number of YouTubes, same size of YouTubes, we could derive uh, 700 megawatt, that is 200 megawatt electric extra power from the uh, same design. Then, then let us come to this stress and fatigue analysis. Here, as per this design is as per ASME, all the nuclear design are as per ASME section 3. Here, the design is as per design by analysis. Here, what we have to do before going for analysis, if we do the analysis using a computer software, here we have to validate the software first. So for that, what we are doing, we are doing n number of uh, uh, known examples in that particular software, even which is available in textbook also. So we are doing n number of uh, uh, problems, and we are comparing the results with the textbook results or with the calculated results uh, with the obtained experimental results. Obtained or predicted results in the computer program. Those results we are giving a allowance of only 2%. If it matches with 2%, then only we are proceeding with the stress analysis. Now here, uh, this results of stress analysis is based on various factors in FEM. So the major factor is choosing the right element type. Okay, so we are choosing for each and every problem, or in a same problem we are coupling different kind of elements. For example, if temperature is being involved, we are selecting either 2D or 3D element with temperature as a degree of freedom in scalar quantities. Then we are coupling this results with the uh, displacement as degree of freedom in vector quantities, another 2D or 3D element. Here we are doing everything through APDL programming. Here we are restricting this aspect ratio with or close to 1 or up to 5. Even the program or FEM allows up to 20. Here we are restricting up to 5 only. And not only that, we are not going for any major assumptions while during this analysis. We are modeling everything, and we are going for machine, or we are creating the modeling or finite element modeling. Here what happens, for example, when we go for cladding or buttering in case of, to avoid lamellar tearing in case of nuclear components, the uh, thermal, uh, the temperature or heat transfer coefficient becomes uh, a what to say factor for producing the stresses. So what happens? It gives many more amount of peak stresses. So I'll explain to the forum, or I suggest the forum in which whenever we do stress and fatigue analysis for nuclear components, not only we have to go for categorization as suggested by ASME section 3, MB 3000. We have to do singularity analysis also. Now, in many of the cases, uh, many written literatures are available in which we could arrive at singularity and we could arrive at the final stresses. Then we can go for categorizing of stresses like primary membrane, primary bending, and peak stresses, and we can compare with the various uh, allowable stresses like SM or 1.5 SM, 3 SM, which is suggested by ASME code. Then we are doing seismic analysis. Here whenever we perform seismic analysis based on the zone in which this nuclear component is going to be installed, we have to take care of all the related piping to the actual component. For example, I have shown here uh, the nuclear steam generator. Here we have to model everything, sir, and we have to consider the masses of all minute internals. Here we have done a huge modeling, and we have made so many couplings, and we have made the pipings. We have considered all the masses of valves, various pumps, various heat exchangers, various headers, which is connected to this equipment. So what happens? Uh, this exhaustive seismic analysis uh, takes huge amount of time in considerably in design. Then first we have to do flow induced vibration analysis. The input for the flow induced vibration analysis is coming from 3D thermohydraulic analysis. So we have to model the entire geometry, and we have to create the flow field. Okay, whenever there is a tube and the fluid is going through this tube, what happens? It tends to vibrate this tube. So in order to arrest, we have to provide some stiffness. It should not affect the thermal expansion of the material, but it should arrest the vibration. For that, we have developed 3D softwares or our own 3D codes in which we have done the analysis, and we have find out the velocity profile at various regions, and based on which we have calculated the critical velocity and the frequency. So the main focus is the material or tube should not experience the critical frequency. To avoid that, what are all the additional supports we have to provide, that we have designed. That much we have to go in detail in design for nuclear components. So these are all some results in 3D thermohydraulic analysis. Not only that, we have to foresee the force-related failure conditions. For example, if we are designing a heat exchanger or pressure vessel, in case of heat exchanger, what happens if the outlet line breaks? So the outside this line, only atmospheric pressure will be there. Inside, the pressure will be very high. So the safety systems may respond within 3 seconds. So within 3 seconds, what will happen? This pressure difference produces a huge amount of uh, uh, external pressure to the components, internals. So our internals to be designed for this post-later failure condition also. In case of our nuclear steam generator, there are two post-later failure conditions. One is feed water line break, and another one is main steam line break. So we have introduced many components in case of this post-lated failure condition analysis. Not only that, we are all aware of Fukushima accident. What happens there? The battery backup was kept at some height, so the tsunami hit it. So that got uh, so due to failure like those incidents, that also has to be taken care in our design uh, based on the accidents which is happening worldwide. So this also we have taken up. Not only we as the nuclear society has taken up as a challenge, and many safety features were introduced. Here, we are predicting stresses. As already I explained that before start of this stress analysis, we validate this computer program. But even after validation, we are doing this stress analysis and we are predicting the stresses. So we are validating the predicted stresses by uh, experimental calculation. For example, the heat exchanger, pressure vessel, or steam generator, we are performing hydro test. In the uh, stage of uh, design, we have predicted some stresses that has to be experimentally matched with the uh, experimental results. So we cannot do experiment in the service life or various service conditions. So what we are taking, we are considering the hydro test. Since we are doing hydro test for of the equipment uh, at our manufacturing works, we are placing strain gauges in the regions where we have seen very high stresses. So there, by many methods like hole drilling or X-ray diffraction technique, we are measuring the strain. From the strain, we are calculating the stresses. So not only the peak stress we are calculating at various levels of hydro test, or the pressure is increased in steps. Okay, in each and every step, we are arriving at a stress cycle. So that we are comparing with the predicted stresses, and our uh, this predicted stresses are validated with the experimentally arrived stresses within 2%. Then only we are allowing our, or we are giving guarantee for 40 years of life for a particular component. So uh, before that, I want to explain you one more thing, sir. That is, for example, we are doing a design of, we are performing a design of tube sheet for a heat exchanger. For doing this tube sheet design, there is in ASME we could not get a calculation or to find out what is the optimum thickness in which we have to start our uh, analysis. Okay, to get an idea, we follow TMA code. So what happens here in case of our steam generator, we have around 2500, exactly 2489. So around 2500 number of U tubes. So there are 5000 holes in the tube sheet. For example, if we over design even 1 mm thickness of tube sheet, what happens? This 1 mm contributes 5000 mm in the tube length. This tube length is already fixed because tube is already manufactured. So what happens? That 5000 mm of tube is being inserted into this tube sheet, which is not contributing for heat transfer. So not only this cost consideration, in structural consideration also, in case of this nuclear, since it involves very high temperature, what happens? It produces a huge amount of thermal stresses to the material. So in case of tube sheet, we have to do huge number of uh, uh, iterations for arriving at an optimum thickness. What happens? Initially in ANSYS, we could not, that control Z concept was there in ANSYS, was not there in ANSYS. So again and again we have to do modeling, we have to check the results, then again we have to remodel. So we started developing this codes in Fortran language, so that by changing the comments in the code, by changing the thickness and by modifying all other parameters like temperature, pressure, because this is one of the critical component which experiences both the operating regimes, that is tube side pressure and temperature also, and shell side pressure and temperature also. So we have done lot of uh, uh, optimization study uh, uh, by changing the parameters in our own code, and we could arrive at a final thickness. So these are all these challenges we face in our uh, design due to various aspects compared to the other uh, fossil power plants. So now, uh, now I thank you one and all for uh, uh, your listening to this presentation. Now I give some request to the forum that we face lot of issues in this nil ductility, transient temperature in design, as well as heat treatment, which this power cut issues and the slower, that is slower rate of cooling and heating affects the binetic materials, like uh, uh, major materials which we use for nuclear applications, like 20 mm MONA 55 material, that is ASME SA 508 grade 3 class 2 or class 1 material. So what happens, this slower rate of heating or cooling affects the ductility of material, which is not addressed in code or not addressed in many of the published journals. And so these two loops were not yet closed. Remaining all based on our experience, we have taken care in our design. I once again thank you very much, sir. Now uh, we can discuss if you have any clarifications or suggestions to make presentation.
Yeah, thank you, Arun Kumar.
Thank you, sir.
I am assuming here that all your difficulties and challenges that you posed is essentially because of the new design for the 700 megawatt reactor, because 500 megawatt also has a steam generator. I don't know whether Trichy was involved then or not, but then what
No,
I see
involved, sir.
Involved, okay, but then you have matured over 500 megawatt to 700 megawatt, or these challenges were not there in 500 megawatt?
No, sir. Actually, these challenges, yes, sir. Actually, rarely we are facing in any one of the component. These challenges are faced in uh, that in 500 megawatt we have not put many power plants, so we could not, or we have not experienced these challenges. Now, since not only the 700 megawatts, are some equipments which we are doing for strategic applications also. This is
Okay.
common for all the nuclear components. So there we face these difficulties.
Okay, okay. So, but I also see that there needs to be a lot of improvement in your NDT techniques also. And let's see if you can get some help from some of the experts in the audience. Before that, let me see if there are any questions you can answer. Sanat Kumar sir, any questions from you? Yeah, somebody has said it's an excellent presentation. Thank you for sharing your experience, Arun Kumar. So there is a compliment for you, Arun Kumar.
Sanat Kumar here.
Yes, Sanat Kumar sir, boliye.
Yeah, actually, I am away from ASME for the past 20 years. So my
comments will be a little bit old. I see that Kiran Dixit is there, so he may be able to give you more accurate thing. But I wanted to say one or two things. Basically, as I remember your presentation, one is this in the form of a suggestion. You can throw it out, no problem. Generally, people throw out my suggestions, so that's not a problem at all for me. So, see, your cladding, I will take that first because that is fresh in my mind. Cladding, I think you are doing 5 mm, if I remember right. So, can you not do it in smaller layers so that you don't get the indications that you are getting in the
Base material.
Base material, subsequent NDT you are getting. So if you made that cladding, I don't know what thickness you put per layer, per pass, how much you are putting, I don't know. But if you are able to reduce the thickness of the per pass thickness, maybe you are all right. That is number one. Number two, you are talking about the NDT or impact energy getting lost. Generally, I don't know whether you are allowed to have a slightly more nickel. Nickel will help you in avoiding this NDT problem, as I remember long. That is number one. Number two is that what is the hot working you are getting in your forging? My metallurgy gurus used to say you should have minimum of 15 hot working from the ingot, when the cast ingot to the forging. You should have something like 15. That's what. I don't know whether you are having like, because your forgings are all very thick, very big. So it may not be possible to get 15, but anyway, that is what it is. For example, in the end fittings, we are also asking for 15. You may know that. So that is one. Thirdly, thirdly, I have talked about hot working. I have talked about forging. Yeah, I suppose this all right. If I have something else, I was thinking of something else I have forgotten. I will come back to you later, but maybe others can say. Thank you.
Yeah.
Sir.
Thank you, sir. Thank you. Yeah, Arun Kumar.
Sir, actually, in cladding, initially you are correct, sir. The layer thickness was around 4 mm. Now it is reduced to 3 mm. The final thickness what we are arriving at is 6 to 8 mm, sir. Initially,
first layer you lower it down. Even 3 mm may be too high. Can you not do 2 mm or 1 mm?
Sir, we will try this.
First layer.
Okay,
then subsequently you put more.
We will try this, sir. We will try this.
Okay.
Oh, thank you.
Sir, then in case of hot working, sir. Sir, here what, sir, actually, whether I can share this in this forum or not. Actually, in the supply which we are getting and the test what they are doing, and they are producing this very good impact values. Then when we do our testing, there we are getting slightly lesser values. So that has to be addressed, that we will take care, sir.
I have a comment. This impact is very sensitive to the longitudinal, the direction in which the rolling or forging is made.
Yes, sir. So, for longitudinal, it is giving very good results, and transverse direction, it is giving.
That is to be expected. Transverse will always.
Yeah. Actually, we are doing a transverse direction only, sir. Since
so
that will give the worst.
Exactly. So you are more pessimistic. That's all right. Fair enough. But yes, you have to give some allowance for that. Okay, then I remember now what is the third point I wanted to say.
Yeah.
I don't know what is the quality of steel you are getting, whether it is a vacuum degassed or ESR or consumable electrode. If you have, for example, ESR quality, you will have much better impact property because hydrogen is not there in that. So can you comment on that?
Sir, actually,
all, thank you.
Okay, sir. We are going ahead with vacuum degassed and fully killed steel.
Can't you do ESR, or
yes,
is
sir,
it
sir.
stupid to do that?
Now, yes, sir. No, sir. Now, recent days, we are proposing for ESR also. So we may get.
So my memory is not all that bad. Okay, thank you.
Mr. Dixit, if you are there, can you give your comment, suggestion. Kiran Dixit.
Yeah, okay. Thanks, Chairman.
Yeah.
Firstly, I would like to compliment BHEL and Mr. Arun Kumar for this presentation, which is in area of design. We had placed order from NPCIL on BHEL about 12 years back with an expectation that these manufacturers also get involved in this process of design and attain expertise so that more and more nuclear industry can grow at a faster pace. From this presentation, I see that, yes, they have attained that expertise and then they have understanding the fundamentals. One thing which I expected, but then probably still was not part of this presentation because it's not part of the work, is that ASME section 3 has got changed substantially in last 10 or 15 years. And I was just curious about what are the new things in that, but maybe that will be a part of some other talk by someone. But for this time, this particular, I would say that whatever, as from NPCIL, whatever our expectations about 12 years back, they seem to have done very well in that respect. He had covered all aspects, including detailed stress analysis, flow-induced vibrations, or seismic analysis, and developing such expertise with various other manufacturers will help NPCIL a great deal in expanding at a faster pace. I'm happy with his presentation. I have no further comments. Thank you.
Thank you. Thank you, sir. Thank you very much. Mehta, sir, you have anything to say? Okay, so thank you, Arun Kumar. Yeah, sir. Mehta, sir.
Well, first of all, again, all of you in complimenting Arun Kumar. One of the important aspects that we have to face is that even though the components are designed for 40 years, but our experience is that most of our power plants go much beyond that. And that depends upon the residual life assessment. And there is a lot of online data collection and analysis. So this provision, of course, is a part of the overall design with the main designer from the Nuclear Power Corporation. But the provision has to be seen and appreciated at appropriate time. So thank you for your presentation.
Thank you very much. Thank you, sir. Thank you, Mr. Arun Kumar, for your presentation and spending time with us, presenting your wonderful work, which was appreciated by experts in this field. So I thank all the members who have attended today and many who will be seeing this presentation on the YouTube, which will be loaded on our website. I thank our President INS, particularly Shri S.K. Mehta, who has been behind all the scientific activity of INS. I thank EC, Executive Committee of INS, for promoting and encouraging to do this webinar on a continuous basis. And I thank Shri Mittal, who is now officiating Secretary and also Treasurer of INS, for having circulated the information about this webinar to a number of people. And I thank Shrimjit Rajgopal, who has been helpful in preparing the posters for us. And lastly, I have to give an announcement about the next webinar, which is on 29th October. It will be given by Dr. Akhilesh Gupta, who is the Secretary, Science and Engineering Research Board in New Delhi, who is speaking on science and technology and innovations in India, Vision 2030 and beyond. So this will be on 29th October, again a Saturday at 5 o'clock. I request all the members to join again on 29th to this new webinar. So I once again thank Arun Kumar, and I now stop this recording with your permission.